Hello, I'm Silvia Zorzetti, a senior engineer at Fermi Lab and the ecosystem lead for the Superconducting Quantum Materials and Systems Center, a Department of Energy National Quantum Information Science Research Center. I am the moderator of the full scientific session, Quantum for the People, Connecting Quantum Information Science and Society. Thank you for joining us. This presentation is one of 3 pre-recorded videos focusing on the speaker material. Before all the panelists come together in February during the live discussion. In this video, our panelist, Charles Brown, will discuss quantum materials and the people who are developing them. Later in this video, Charles and I will have a conversation on the topic. Charles is part of the Stamper-Kern group at the University of California, Berkeley, an institutional partner of the DOE's Quantum System Accelerator. As a National Quantum Information Science Research Center, QSA is catalyzing national leadership to co-design the algorithm, quantum devices, and engineering solutions needed to deliver certified quantum advantage for DOE scientific applications. The center is co-led by Lawrence Berkeley and Sandia National Laboratories, and is integrated by 13 other partners. Welcome, Charles.
Hi, thank you, Silvia and AAAS for hosting this scientific session on engaging people in quantum information science and engineering. As the title suggests, Quantum Opportunities, the Quantum Material Revolution, Science and Society. I will tell you a bit about quantum materials and the opportunities that they will afford us, and really how this important budding field is connected to overall society. So what is a quantum material? Well, it's a material in which quantum mechanics gives rise to incredible properties. Quantum materials have properties that cannot be described with classical physics. In practice, at least in solid form, they're solids with exotic physical properties that emerge from the quantum mechanical properties of their constituent electrons. Or in systems like the ones that I work in, we instead use really cold gases that behave quantum mechanically, and we put them into lattices made out of light in order to simulate quantum materials. Okay, but as I mentioned, a quantum material cannot be described by classical physics. Instead, you need something like the Schrodinger equation, where essentially up to some constant, the thing to the left of the d over dt, the time rate change of the state of your system psi is just given by something h. This encodes the energy characteristics of your system multiplied by the state of your system. And so a really compact equation like this can tell you about a whole host of very fascinating quantum-based properties of materials, like the ones I have on the right. The material graphene, for example, a single atom thick layer of carbon atoms in a hexagonal direction or arrangement, or a honeycomb arrangement, where electrons zip around this material at incredible speeds, right? Incredible speeds compared to sort of state-of-the-art electronics based in silicon, which is the material we use to build most of our really high-quality electronics. Or these other interesting materials, KVSB, or its full name, potassium, vanadium, antimony. That's actually a superconductor at very low temperatures, near absolute zero. A superconductor being a material that can allow electricity to flow through it with essentially zero loss, okay? So, what is it that makes these quantum materials unique? It's the fact that they benefit from coherence and entanglement. Coherence being the property of a state of a system, the way that you describe the system, being wave-like, so that waves can add constructively or destructively, they can interfere with each other, sort of like light does. Or entanglement, where instead of being able to describe the state of, say, a single electron among many, say, in your graphene, you have to write an entangled state that encodes information about how all the electrons are sort of interacting with each other. Right? Okay. Quantum materials have immense scientific and technological potential. And so, I really like to think about these in these sort of two categories, but of course, there's quite a bit of overlap between the two. On the scientific potential side, there are quantum fluctuations in order, where we sort of think about how these spontaneous changes in physical properties of a material, these quantum fluctuations, lead to, say, electrons being ordered in some way in a material that leads to some new and exotic state of matter. Or the role of mathematical topology, this field that tells you about how surfaces are connected to each other and the sort of geometry of surfaces and how that relates to something in a material like the pathway that electricity can flow, right? And where it flows on a material. And even more generally, how to manipulate quantum effects like coherence and entanglement. On the technological potential side, there's a huge goal of building a quantum computer. When you think about quantum materials, these materials could help aid us in building this quantum computer, a device that instead of like a classical computer that has bits that take on values of 0 or 1, a quantum computer's bits can be combinations of 0 and 1. And this will allow us to solve some class of problems that are intractable even with today's most powerful supercomputers. Right? You also have quantum enhanced sensors, or what people might call quantum sensors, which capitalize on quantum effects. And along with their strong sensitivity to external disturbances, is where a lot of the power comes from. They can make highly accurate measurements of electromagnetic fields, time and frequency, displacement and rotations, and temperature and pressure. Lastly, on this slide, but certainly not least, there's this really important goal of power transmission. I mentioned superconductors on the previous slide. These are materials that allow electricity to flow with essentially zero resistance, zero loss. Imagine if we could have such a material not at nearly the coldest temperature possible set by quantum mechanics, but up near room temperature. Imagine if we can have superconductors to build our power lines with, right? This quantum material that allows electricity to flow with zero loss could drastically reduce the cost of power transmission and really be transformative for society. It's important to think about where quantum materials are made, and overall quantum materials and generally quantum technology are being developed all over the world. Certainly they're being developed here in the United States, and in the United States, some of the most important global players are here doing a lot of important work. This happens at, for example, the national labs, the Department of Energy National Labs, happens in academia, in particular associated with the Department of Energy funded national quantum centers like the one here at Berkeley, the QSA. But really, this initiative to develop quantum materials and technology is happening all over the world. But it's important to think about by whom, right? If you sort of look at any one of these individual societies or segments of societies, what you find is that there's a majority group, which represents a sort of small proportion of the number of identities of people that make up the nation or the segment of the nation that sort of have all of the say in what kind of problems that the community thinks about, which direction it goes, et cetera. And it's important to note that there's an incredible amount of money flowing into quantum science and engineering, to the tune of billions. For example, I mentioned these Department of Energy national quantum centers. There are 5 of them, each funded at the level of 115 million over 5 years. And that's not all the money. So, there's a lot of really important investment being done into quantum science and engineering. And this is great because this sort of investment is really going to allow us to move the goals of the field forward. But again, we need to be thinking about who is doing the work, who's involved, and who has a voice. And so to sort of, describe one of the issues that I see as it relates to representation, that can be done in this picture. So this is a picture from an important conference in the field in which I did my PhD, one of the many kind of quantum fields. And the striking thing that you'll notice about this picture is that there's about 150 people in it, most of which are white and East Asian. And there's only one Black person, and that's me. And while this is but a single example of a conference photo from a quantum workshop or a quantum conference, if you were to go to these conferences and look around, you would find that this is the sort of typical breakdown of identities, be they race or gender or ability, disability status, I should say, excuse me, or other underrepresented identities in STEM, in particular in quantum information science and engineering. And before I move on, I wanted to make a point that, I've gone through quite a bit of detail along with Jessica Escobar talking about these sorts of issues. So if you're interested in this, please see Part of the Revolution, Black Representation in AI and Quantum Information, which was written in Physics Today. So moving forward, I want to make the point that the practice of quantum science and engineering should be accessible and equitable. Right? There's a lot of talk about the case for diversity, and it is, in my opinion, and several other people's opinion, that the case for diversity shouldn't solely rest on the idea that we could be so much more productive if we had more diversity, right? The inclusion of underrepresented folks cannot solely be to increase production, right? We should also have access to STEM, and specifically quantum information science and engineering, simply because it is a wonderful endeavor that's part of human expression and how we see ourselves fitting into the larger picture of the universe, right? When I think about quantum information science and engineering, I see it as an incredibly exciting human endeavor, right? I mentioned it's part of human expression, right? And it turns out that the practice of science is cultural. It matters who is asking the questions and from what framework they are thinking about both the questions and the answers to their questions. It also matters who is making the technology and who is affected by that technology and how. One example of people being affected by technology and maybe the group of people developing the technology not thinking carefully enough about it is in pulse oximeters. These flashing light systems, say on the back of your smartwatch that measures your heart rate, that works well on light skin and for a long time did not work well on dark skin, right? I had one of these Fitbits that could not measure my heart rate. I've also had the experience of going to one of these restrooms in, say, an airport, and the sensor cannot detect my skin, and so I can't turn on the sink. While these are small examples of problems, this sort of thing really matters when we start to talk about artificial intelligence and quantum mechanics and how they work together, and how, it matters what sort of data is being used to train the system. Okay. Finally, it's also important to think about economic opportunities. Here I have a plot of what is referred to as early career degree holders. These are people that have had their PhDs for 10 years or less. And these people are incredibly important because they do a lot of the shaping of the sort of problems that are deemed important in a field and the overall direction of the field, where the money is going, what sort of problems are getting the money. And what you see when you look at this field, just as it relates to ethnic identities, right? A majority of these people are white, a large majority are white. The next largest group is Asian. And so if you sort of add up everybody that is white and East Asian, you see this is sort of 80% of early career PhD holders that are really driving the direction of the field. They come from but two groups of many different identity groups, okay? And this is not only important because of sort of who is asking the questions or what's deemed important, but also because of socioeconomic mobility, right? We live in a very technology-driven society where proximity to STEM grants a lot of economic mobility. It allows you to elevate yourself in society. It allows you to access potentially to sort of wages that allow you to live a more liberated life, right? So it's important that it's not just a small proportion of the identity groups here, say in the United States, that have access to such socioeconomic mobility. Okay, so in closing, I want to say that it's important that we not set in stone, wildly unrepresentative demographics of who does quantum information science and engineering compared to who exists in the larger society, say in the United States. In doing so, we risk actively excluding large groups of people from participating in this exploding, literally society-altering event in human history. that is the explosion of quantum science and engineering. A representative quantum workforce could bring so much good to our society. We'll develop new lines of scientific inquiry and tech development that is representative of society and is well positioned to tackle society's biggest problems. I mentioned, there are billions of dollars, millions of dollars, billions of dollars are flowing, and the long-term teams are being defined right now. And I would say that regardless of identity, I'll just say this: regardless of identity, professional and economic mobility through quantum information science and engineering must be accessible to wide ranges of people to build a powerful workforce for societal betterment. And we have the opportunity to, while quantum information science and engineering is still rapidly growing, we have the opportunity to sort of right the path. But we must act to do so, and it's really important that we do so now.
Thank you, Charles. Nice presentation, and thank you for the insightful contents on quantum materials and also diversity and inclusion. So I have a few questions for you, and in fact, I want to start from your last slide. I want to learn about your perspective about what we as employers, as national laboratories, academic institution, and research center can do to increase the representation of underrepresented demographic group. Not only for offering opportunities for higher educated people, but also who belong in this to these groups, but also to increase the opportunities, the awareness and the knowledge of young kids who are in school and are interested in STEM.
Yeah, so this is such an important question. I really appreciate being asked this question. And I think this is something I have quite a bit to say about. As already mentioned, the Department of Energy, National Quantum Information Science Research Centers, each of which received $115 million over 5 years to carry out this quantum research, along with multiple NSF quantum centers, those being funded at $25 million over 5 years. These groups are very well positioned to use these incredible financial resources, right? We're talking about nearly $1 billion already to create and support environments, free of discrimination that often hold back talented individuals from underrepresented groups, and to provide early exposure and training to students from these underrepresented groups. For example, well-funded research exchange programs that grant students, especially younger ones with experience in quantum information science and engineering, led by mentors who don't view these students as deficient, who don't hold negative socially driven views regarding these students' fixed abilities, could really help spark an interest in quantum information science and engineering, or deepen an existing interest that these students already have in this important field, and help students to start forming scientific identity and community around quantum information science and engineering, all of which have been crucially important anchors for everyone in the field. Right? I think we should also be thinking about this question and how to address it in the sort of longer term. And in doing so, we should consider how we recruit young students, really maybe as young as in the 6th grade. Young underrepresented students, even in elementary school, have deep interests in STEM fields, even if they can't yet articulate which field they're most interested in. And this presents an opportunity for us quantum information science and engineering researchers to reach out and connect with them early on, to further deepen their interests, to inspire them, to be role models for them. Perhaps we need a spokesperson that is like the Carl Sagan of quantum information science and engineering, that is highly visible and interacts with many people with varied backgrounds, so that young people can see themselves in that spokesperson, or see themselves as someone who can do what the spokesperson does. Aside from such a spokesperson, the DOE and NSF quantum centers have involved with them many of the most important global players in quantum science and engineering. Right? It could be quite impactful if these researchers went out into society, gave public lectures at libraries and schools, and invited students to come see the labs and meet scientists, maybe even have the students get some kind of hands-on experience. Like, these sorts of experiences are completely life-altering for young people. And, lastly, there are other important initiatives happening, like the $100 million IBM HBCU Quantum Center. For those who are unaware, HBCU stands for Historically Black Colleges and Universities. This center aims to prepare and develop talent at HBCUs from all STEM disciplines for the quantum future. It emphasizes the power of community and focuses on developing students through support and funding for research opportunities, curriculum development, and workforce advocacy. Right, the center also aims to strengthen research efforts of faculty at HBCUs in quantum information science and engineering, and empowers HBCUs to lead in the newly emerging field and impact the greater Black community. Right, so this sort of initiative has the potential to be truly, truly transformative.
Thank you, Charles. Yeah, a lot of, again, insights, and probably we should talk more about that. Now, going back to the quantum materials that you just presented, what is the main technological bottleneck in the development of quantum materials or related applications?
Yeah, so when I think about this question, I think the answer, at least in my mind, is temperature. So whether you work on quantum materials in a solid state, like on graphene or the potassium, vanadium, antimony material that I described earlier, or if you do quantum materials like I do, where you make these ultra cold quantum gases that are trapped in lattices made of light that simulate quantum materials, it's almost always the case that temperature is a problem for you, right? So these systems have to be very cold and isolated from their environment. And that's because if you don't do so, you limit those important quantum effects, coherence and entanglement. And that's because interactions between the environment, say energy exchange between the quantum system you want to simulate or that quantum material, exchanging energy with the environment, that tends to destroy any kind of interesting quantum effects, any kind of interesting advantages of quantum mechanics that you would gain. And so, yeah, right now, it is the case that all the work with quantum materials is done in very cold temperatures, So on the Fahrenheit scale, something like, negative 455 degrees or something like this. And, I mentioned power transmission with superconductors. Right now, we're pretty far away from having a superconductor at a high temperature. But again, if we could ever achieve such a thing, that will really change society.
Thank you. The next questions are more on, your path and education, and I think this could be also inspirational for the people, and in particular students or young researchers who are listening to us. Is there a scientist or a researcher who inspired your career?
Yeah, absolutely. So that's an interesting question for me because I couldn't possibly name a single person in doing so. I really can't say there's a single scientist that has inspired my career. And that's because my perception of my place in all of this, in physics as a discipline, as a scientist in the world, it's really evolved and it continues to evolve. So, like many of us at a young age, I was struck by Einstein's work and the kinds of problems people could think about in trying to understand nature. I was completely obsessed with black holes when I was a kid. And, it wasn't just black holes. Einstein did lots of different physics. And so me sort of learning about what Einstein did was really inspiring. I think beyond that, my first quantum physics teacher, Professor Jim Kakalios at the University of Minnesota, he was an excellent teacher. And he really sparked my interest in quantum mechanics. This sort of makes sense. He wrote this popular book, The Physics of Superheroes. And so science communication was sort of already in his blood. And I think having someone like that teach me quantum mechanics was incredibly inspiring. But I've also been deeply inspired by other people. Professor Jack Harris, Professor Chanda Prescott-Weinstein, and Professor Jelida Eisler, who really helped me to understand the importance of the science that I do and my role in doing it and the sort of stake I have as a Black man in the United States who is a physicist doing this important work. And also along that same line, astrophysics professor John Johnson. All these people have been incredibly inspiring for me in my career and continue to be.
And one last question. Is there a book or a movie or lecture on quantum science who will you recommend to people?
Yeah. So, I mean, I guess as far as books go, I have a sort of fun recommendation. I really like this book, How to Teach Quantum Physics to Your Dog by Chad Orzo. It's a humorous book that contains a nice amount of pedagogy describing wave particle duality, entanglement, quantum tunneling, but in a fun way with the love of the dog. I'd also recommend The Disordered Cosmos by Chandra Prescott Weinstein, a book that's both about quantum field theory and its connection to cosmology, but also about the academic discipline of physics and how it can and needs to be better for the betterment of its practitioners, for the betterment of society, and the overall discipline of physics.
Thank you, Charles. Thank you for your presentation and for answering these questions. This is a reminder that this is only one of 3 spotlight videos focusing on the individual work of the speakers before they will come together in February in the live panel, Quantum for the People, Connecting Quantum Information Science and Society. Please check the AAAS annual meeting website for the panel's date and time. Thanks to the audience for your attention. We'll see you live in February.